Okay, in this video, let's derive the expression for the speed of the mass as it passes vertical equilibrium. So at equilibrium, it gets a little more complicated. So if we just redraw this for the sake of making it easier to see, we have the unstretched spring, and then we have the stretched spring at equilibrium, and then we have the max stretch spring. And if we look at these positions, we figured out in the last problem that the stretch at equilibrium, which I'll call this XEQ, is half the max stretch, which means the height this is above the lowest point. So the height of equilibrium above the lowest point is also XEQ. So this is at the midway point of the two vertically. Now, if we want to derive an expression, we need to compare the total mechanical energy at equilibrium to the total mechanical energy at any other known point. So let's start by looking at the total mechanical energy at equilibrium. Let's call this position 2 to make it a little easier to write down. So at position 2 at equilibrium, the total mechanical energy will be the gravitational potential, not S, 2, at 2. Now, since the lower position here, the max stretch position, is our zero potential, I do have some gravitational potential at position equilibrium relative to my lowest point, so I have to include that, plus the kinetic energy at 2. It will be moving as it slides past equilibrium, and actually will reach its max speed since the net force is downward until it stretches past, and then the net force is upward, then downward, then upward, and so it will reach its max speed here. So it is moving. It does have some velocity, v2, at equilibrium, plus its spring potential at position 2. Now, since this is unstretched here, my initial position, that's max stretch, it is stretched relative to its unstretched length, so I will have some spring. So I have to account for all three types of energy at equilibrium. That's what makes it a little more complicated. So let's write those out in terms of quantities we know or we can relate to. We know that UG at 2 is going to be the mass times G. Now let's write this as the equilibrium stretch, because we know this height will be the same as this stretch relative to my gravitational potential, plus 1/2 times mass times whatever that v2 is squared, and that's really what we're solving for, the speed as it passes equilibrium, plus my spring potential, which is 0 here, but 1/2 kx equilibrium squared. Now I know I was using delta x equilibrium, and I'm now using x equilibrium. So just to be clear, these are the same thing. Whether you use the delta or just call it x, it's up to you. Now I need to refer that to some other position where I know the energy. And I'm going to look at my initial position where I had fully gravitational potential. So the energy initial was mg times delta y naught. But then we made a connection here. We saw that delta y naught was the same as the max stretch, which is the same as double the equilibrium stretch here. So I'm going to write this E sub naught as mg times 2 stretch at equilibrium from this substitution. And then we know that because of conservation of energy, conservation of mechanical energy, that delta E from any two positions has to be 0. No other non-conservative forces are doing work on the system, therefore the system's mechanical energy will remain constant. So this tells me that the energy initial has to equal the energy at position 2, total mechanical energy that is. And so I'm going to set this up as mg times 2 x at equilibrium has to equal mg x equilibrium plus 1/2 mv2 squared plus 1/2 k x equilibrium squared. And now I have kind of a mess. I have an equation that has V2 in it, and it has a bunch of other known quantities. I know X equilibrium, I'll know K and mass and G. I guess I should say don't know that I know them, but if I knew the mass and the stretch and gravity and K, I could figure out this maximum speed. So let me get the kinetic energy term by itself. So I'm going to subtract this over, subtract that over. So mg times 2 x equilibrium minus mg times x equilibrium is just mg times x equilibrium. So that's this minus this. Minus a 1/2 k x equilibrium squared equals a 1/2 mv2 squared. And so now to simplify this, I can multiply both sides by 2, so this becomes 2 mg, and this 1/2 cancels. I can divide by m. I divide this by m, divide this by m, so the m cancels on this one, but I have it here, and then I'm going to have to square root the whole thing. So let's write this out in some simplified form. I'm going to have 2g times x equilibrium minus, now the 2 canceled the half, but I have the mass here, k over mass times x equilibrium squared, and that whole thing square rooted. And oops, I'm off the screen there. There we go. So that is deriving an expression for the speed at equilibrium using conservation of mechanical energy, relating the total mechanical energy at equilibrium to the equilibrium at some other known position, which I chose to be the max height at the initial position. You could have chose max stretch as well. You could have related it to position 1 and then have used 1/2 k times delta x max squared. You could have done it multiple ways, but this is the way I did it. And there is your example.